Hello students, welcome to Math Center Web Coaching. Today I'm going to start with the topic matrix. Let's see what does it means. A matrix is a rectangular array of numbers. The size or a dimension of a matrix is defined by the number of rows and columns it contains. Now basically matrix is nothing but the arrangement of the numbers in a rectangular form. Okay. Let's see one example. Suppose I want to arrange these 9 numbers in a matrix form or in a rectangular form. Then what will we do? I will do in this way. Suppose 1, 2, 3, 4, 5, 6, 7, 8, 9. I arrange this way and then I put the bracket over here, right? Bracketed notation. And this bracketed notation is nothing but the matrix, or you can say this notation is used to indicate the matrix. Okay. Now matrix is always represented by the capital letters A, and these numbers, all these numbers are called as the elements of the matrix. So here my A is my matrix and 1, 2, 3, 4, 5, 6, 7, 8, 9 are the elements of the matrix A. Okay. Now next, the size and dimension of the matrix is defined by the number of rows and columns it contains. Now what does it mean, rows and columns? Rows are nothing but the horizontal arrangement of the numbers and columns are nothing but the vertical arrangement of the numbers. Okay. Now here rows, now horizontal arrangement here 1, 2, 3. Okay. They are arranged in a horizontal manner. So this is my first row. 4, 5, 6. This is my second row. And 7, 8, 9. This is my third row. Okay. Now, what about columns? The arrangement of the numbers in a vertical manner. So, 1, 4, 7, 1, 4, 7. This is my first row, first column. 2, 5, 8. This is my second column. 3, 6, 9. This is my third column. Okay. So, just I mention here C1. This is C2. That is second column. And C3. This is my third column. Now, the size and dimension of the matrix is defined by number of rows and columns. Now in this matrix, we have 3 rows and 3 columns. So what is the size of the matrix? The size of the matrix, or you can say the dimension of the matrix, or you can say the order of the matrix. Okay, so order of the matrix is nothing but 3 rows and 3 columns. Now how will we indicate, how will we represent this order? Always write the order of the matrix at the right bottom of this matrix. So here I indicate this 3 cross 3. This is nothing but the order, or you can say the size of this order matrix. Okay. So what is the size? The size is 3 by 3. So 3 by 3 is nothing but 3 rows and 3 columns. Okay. Now if you can see, I highlighted these points. There is 1, 5 and 9. These numbers. Now 1 is the first element of this matrix and 9 is the last element of the matrix. Okay, so this is my principal, or you can say leading diagonal, principal diagonal. Okay, why? Because it covers the first element of the matrix and last element of the matrix, that is 9. So this is my principal diagonal or leading diagonal. So the numbers 1, 5 and 9 are called as diagonal elements, and the rest of the numbers, that is 2, 3, 6 and 4, 7, 8 are called as non-diagonal element. Okay. Now suppose I want to arrange the n elements in m and n rows, okay, in general form. Then how will we do that? Arrange n numbers in m rows and n columns. So I take the matrix B here, okay. Then A11, A12, A1n, A21, A22, A2n, and so on up to AMN. So what it indicates, actually A11, A12, A1n, these all are nothing but the elements of the matrix B. But if you have noticed here, 1, 1, 1, 2, 1n, these are the suffixes, and what it indicates? It indicates the position of that element. Now here A11. So A11 is nothing but this 1, 1 represents the position of this number, that is in this one element is in the first row and first column of the matrix B. Now A12. The 1, 2, the first row and second column. So this element is in the first row and second column of this matrix B. Okay, and so on. Now in this matrix we have mn numbers. Okay, so the order of this matrix is m cross n, and always remember this first quantity represents the number of rows and second quantity represents the number of columns. So m cross n, that means the order of this element B. So this matrix B contains the mn elements. Okay, now suppose I want to represent this matrix in an element wise, then we can write B is equal to this matrix Aij, and order of the matrix is Mn. Now what it indicates? Now I and J. So I and J is nothing but the position. It indicates this position of this element A in ith row and in jth column, where I row is going from 1 to m and j is going from 1 to n. Okay, so this is the smallest representation of this matrix. Okay, Aij in general form. Now we move towards, this is the basic idea of the matrix definition and introduction of the matrix. Now we move towards the types of the matrices. Okay, there are so many types of the matrices. Okay, the first matrix, the row matrix. A row matrix is the matrix which with only one row. Now with only one row means the matrix having only one row is nothing but the row matrix. Okay, so here this is my matrix 2, 3. Okay, this matrix contains only one row. So in order you can see I write here 1 cross 2. So 1 is nothing but number of rows and 2 is nothing but the number of columns. Okay, so 2, 3. Now this example. Okay, 4, 6 and 8. So this is the row matrix because it contains only one row. So the order of this matrix is 1 cross 3. Okay. Now next, column matrix. Column matrix is a matrix with only one column. Right? So 5, 4, this matrix 5, 4, and this matrix is of order 2 cross 1. So there are 2 rows and 1 column. Right? This matrix 8, 9, 6. This matrix is of order 3 cross 1, 3 rows and 1 column. Okay. Now zero matrix. Zero matrix, the name itself suggests, okay, the meaning of that matrix. So zero matrix, or you can say a null matrix, is a matrix which or that has all its elements 0. Okay, the matrix having all the elements are 0 is nothing but your zero matrix. So this is my zero matrix. This is also my zero matrix. This is of order 2 by 2. 2 rows, 2 columns. 3 rows, 3 columns. See, 3 by 3. Okay. Next, the square matrix. A square matrix is a matrix with an equal number of rows and columns. The matrix is called square matrix when the number of rows is equal to the number of columns. So number of rows and number of columns, if they are equal, then that matrix is nothing but the square matrix. So in this example, 2, 3, 7, 9, 2 cross 2, 2 cross 2, because we have 2 rows, that is 2, 3, and second row is 7, 9, and first column is 2, 7, second column is 3, 9. That is 2 rows, 2 columns, 3 rows, 3 columns, 3 columns. Okay. Now we move towards the next definition, diagonal matrix. So what is diagonal matrix? Now again, this name itself suggests the meaning of that matrix. A diagonal matrix is a square matrix that has all its elements 0 except for those in the diagonal from top left to bottom right, which is known as the leading diagonal of the matrix. Now, in a simpler manner, the diagonal matrix is nothing but all the non-diagonal elements are 0 and the diagonal elements are other than 0. Okay, that means except 0. So, diagonal contains the except 0 numbers and non-diagonal elements are 0. Okay, so in diagonal matrix, The non-diagonal elements are 0 except diagonal elements. Okay. Next, the scalar matrix. A scalar matrix is a diagonal matrix. First, it is a diagonal matrix. So obviously, non-diagonal elements are 0. Okay. And what is the condition on diagonal elements? Let's see. A scalar matrix is a diagonal matrix where all the diagonal elements are equal. For example, this. Okay. So first, as this is a diagonal matrix, so non-diagonal elements, if you can see here, non-diagonal elements are 0. But what is the condition on diagonal elements? The diagonal elements are equal. So same number. Okay. So this is my scalar matrix. Now next, upper triangular matrix. An upper triangular matrix is a square matrix where all the elements located below the diagonal are zeros. Now upper triangular matrix. So upper triangular matrix means the elements below the diagonal are 0. Okay, so this is my diagonal elements 1, 2, 3. Okay, this is my diagonal, and the elements located below the diagonal elements, okay, below the diagonal are 0. So this triangle is 0 for upper triangular matrix. And for lower triangular matrix, a lower triangular matrix is a square matrix where all the elements located above the diagonal are zeros. So here you can see 1, 2, 3 our diagonal elements, and this upper triangle, elements. Okay, these are all 0. So the elements which are located above the diagonal are 0. Now unit matrix, the name itself suggests the meaning. A unit matrix is a diagonal matrix whose elements in the diagonal are all 1. Okay, so diagonal elements are 1 and non-diagonal elements are 0. Now unit matrix is represented by capital I. Okay, and suppose this matrix and the given matrix is of order 2 by 2, then you can write I2. Or suppose if your given matrix is of order 3 by 3, you can write I3, and so on. Suppose the given matrix is n by n order, then you can write I to the suffix n. Okay, so the unit matrix is nothing but diagonal elements are 1 and non-diagonal elements are 0, because as it is diagonal matrix, right? Next, singular matrix. Now singularity of the matrix is depend upon the determinant. Okay, in 11th standard you must have come across with the concept of determinants, right? If the value of this determinant is equal to 0, value of the given matrix, okay, the value of the given determinant A is equal to 0, then it is called as singular matrix. The square matrix that does not have a matrix inverse, right? Because a matrix is a singular if and only if determinant is 0. Its determinant is 0. Now, non-singular matrix. A non-singular matrix is a square one whose determinant is not 0, right? Determinant. If the value of this matrix and of its determinant is not equal to 0, then it is non-singular matrix, and then only you can find out. Okay, this is the necessary and sufficient condition to find out the inverse of the matrix. We are going to see all that in our next videos actually. Now next definition, transpose of a matrix. A transpose of a matrix is a matrix obtained form a given matrix by interchanging rows and columns, and it is denoted by A raised to T, right? So transpose of the matrix is nothing but we are going to, or we can say we are interchanging rows and columns of the matrix. So my first row becomes my first column, second row becomes my second column, third row becomes third column, right? So this is nothing but a transpose of the matrix, and we indicate that transpose of the given matrix is A raised to T, or you can write small t also, or A dash, A raised to dash. Okay, so here for example, suppose A is equal to this matrix 3, 2, 4, 1, 5, 6 and 8, 3 is 2, right? So I want to find out the transpose of this matrix. So by the definition, what is transpose? So given matrix by interchanging the rows and columns. So we are going to interchange the rows and columns. So here 3, 2, 4, this is my first row, right? Now transpose, this is my first column, right? So I write here 3, 2, 4. Now my second row 1, 5, 6. This is my second row. Now this becomes my second column in A transpose, that is A raised to T. There is 1, 5, 6. And for third row 8, 3, 2. This is my third row, and here that becomes my third column 8, 3, 2. Okay. Now this is my transpose of the matrix A, and it indicates by A raised to T. Okay. So this is transpose of the matrix. Next, symmetric matrix. Now what is symmetric matrix? The name itself suggests the meaning. Okay, so symmetricity. So what it indicates? The matrix A is a symmetric if it is equal to its transpose or A raised to T. I should write here A raised to T. Okay, A is equal to AT. Matrix A is symmetric if and only if the sweeping indices doesn't change its components. That means Aij is equal to Aji, means A is equal to A raised to T. So symmetric, when the matrix is symmetric, if it is equal to its transpose. Okay, now symmetricity, if you can see here, 1, 5, 6, this is my diagonal, right? Sorry. Okay, so 1, 5 and 6, this is my diagonal elements. Okay, and now you can see non-diagonal elements 2, 3, 8 and 2, 3, 8, right? So this is the symmetric matrix, because if I want to take the transpose of this matrix, again my first row, that is 1, 2, 3, right? That is my first column of A raised to T transpose, right? Now 2, 5, 8. This is the second row of the matrix A, but in A transpose 2, 5, 8. Again, this is my column, second column of the A raised to T, that is transpose. So symmetric matrix, this is symmetricity is with respect to, okay, the non-diagonal elements and with respect to diagonal. So main diagonal, leading diagonal, okay. Now skew-symmetric matrix. A matrix is skew-symmetric if and only if it is opposite to its transpose. All main diagonal elements of a skew-symmetric matrix are 0, and every square matrix is the sum in a unique way of a symmetric and skew-symmetric matrix. Now let's see one by one. So skew-symmetric matrix. Now in symmetric matrix, we can say A is equal to its transpose, and in skew-symmetric matrix, minus of A, negation of the given matrix, is equal to the transpose of the matrix. Okay, so obviously in symmetric matrix, we have seen that Aij is equal to Aj, right? But in this skew-symmetric matrix, Aij is equal to negation of Aj. So this, for example, this matrix is skew-symmetric. And one more condition is here, that is all main diagonal elements of the skew-symmetric matrix are 0. Why? Because Aij is equal to minus of Aj. And suppose I am going to add this, then it will become 0, right? So that means this 0, diagonal elements of the skew-symmetric matrix are always equal to 0, and non-diagonal elements are nothing but the negation or opposite of each other. Okay. Now next, conjugate of a matrix. A conjugate matrix is obtained from a given matrix by replacing each element by its complex conjugate. Now what is complex conjugate? Okay, so suppose z is equal to x plus iy is my complex number, then x is my real number, real part of the complex number, and y is my imaginary part of the complex number. Now, how will we calculate the complex conjugate? X plus iy, that is the real part x as it is. Now we change the sign of the imaginary part, that is iy minus, right? So z is equal to x plus iy, this is my complex number, and complex conjugate of this z is denoted by z bar equal to x minus ry. So we change the sign of the imaginary part. Okay. Now the same condition apply. We are going to apply in matrix. So conjugate of a matrix is denoted by a bar, like this, z bar, right? Then how we calculate, or how will we find out this conjugate of a matrix? By replacing each element by its complex conjugate. Okay, so let's see. Suppose this is my A matrix, that is 2, 1 plus I, minus I, 3 plus I, 0, 2 minus 3I, 5I, and 4. Then the conjugate of this matrix is denoted by A bar. Okay, and now we are going to obtain this or find out this A bar matrix. Okay, so for this, what we are going to do? 2. This is real number. Okay, so 2 as it is. Then 1 plus I. This is my complex number, right? So complex conjugate of 1 plus I is 1 minus I. Complex conjugate of I is minus I. Now minus I. Complex conjugate of minus I is I. Second, 3I plus 2, right? So 3I is the imaginary part. So we have to change the sign of 3I, imaginary part. So this will becomes minus 3I plus 2, 0 as it is. Then last row, this 2 minus 3I. The complex conjugate of 2 minus 3I is 2 plus 3I. Then complex conjugate of 5I is minus 5I, and complex conjugate of 4 is 4. Okay, because 4 can be expressed as 4 plus 0I, right? So this is my conjugate of a matrix. Okay, now next, transpose conjugate of a matrix. Now again, this name itself suggests what we are going to do, right? So if a matrix with the entries, or you can say the elements from the field, then the conjugate transpose of its is obtained by taking the complex conjugate of each entry in and then transposing. Okay, so what it indicates? It suggests that transpose conjugate. So first we have to find out the conjugate of the matrix by this procedure, and then after after obtaining that conjugate matrix, we have to transpose that matrix, and then we will get transpose conjugate of a matrix. Okay, first step we have to find out the conjugate matrix and then find out the transpose of that conjugate matrix. Then we will get this A theta, because transpose conjugate of a matrix is represented by A raised to theta or A star, or you can say A bar raised to t or dash. Okay. For example, suppose A is equal to 4 plus 2 plus 3i, then 3i, 2 plus I, right? This is my given matrix. Now, by definition, first we find out the conjugate of the matrix. Now, what is conjugate of the matrix? Conjugate is nothing but the every element of the given matrix we are going to replace by the complex conjugate of the number, or the complex conjugate of that number. Okay, so first we find out the A bar. So first, for real number as it is, now 2 plus 3i, right? This number 2 plus 3i. The complex conjugate of this number is 2 minus 3i. Now complex conjugate of 3i is minus 3i, and complex conjugate of 2 plus I is 2 minus I, right? So this is our A bar. That means conjugate of a matrix. Now transpose conjugate of a matrix. So we are going to transpose this matrix. That is, transpose is nothing but interchanging rows and columns. So my first row 4 and 2 minus 3i will become my first column. So here this is my 4, 2 minus 3i, and my second row will become second column. So minus 3i minus 2. Minus 3i, 2 minus I, right? So this is nothing but a raised to theta. That means transpose conjugate of a matrix. Okay. Now this is the property actually. A raised to theta is equal to A. So transpose conjugate of the matrix and again transpose conjugate of this matrix A raised to theta is always equal to that matrix, given matrix A itself. Okay. Next, Hermitian matrix. A Hermitian matrix, or you can say self-adjoint matrix, is a complex square matrix and that is equal to its own conjugate transpose. That means if the matrix is equal to its transpose conjugate, that is A, if A is equal to A raised to theta, then that matrix is called Hermitian matrix. Okay. And in element wise form, if you can if you have to write down in a element wise form, then you can write Aij is equal to Aj bar, means every element here, right, given matrix is equal to its transpose conjugate matrix. Okay, A is equal to A raised to theta. Now what are the notes or points you can say? First, the entries, or you can say the elements of the diagonal of a Hermitian matrix are always real. If you can see here, the diagonal elements, just a sec, diagonal elements, that is 2, 4, 3 and 4 are real. And what about non-diagonal? The non-diagonal elements are complex conjugate of each other. Okay. So complex conjugate, if you can see here, non-diagonal elements are 3 plus 2i, I and 5. So complex conjugate of 3 plus 2i is 3 minus 2i. Complex conjugate of this I is minus I. And complex conjugate of 5 is 5. Okay. So this is the Hermitian matrix. So Hermitian matrix is nothing but A is equal to A raised to theta. Okay. So A raised to theta is nothing but transpose of a conjugate matrix. Okay. Next, now skew-Hermitian matrix. Now skew-Hermitian matrix, when the skew-Hermitian matrix, a square matrix A is a skew-Hermitian if it is equal to the negation of its complex conjugate transpose. Right? 1 minute. I have to write here A raised to theta. Okay, so negation. So skew-Hermitian is nothing but minus of A is equal to A raised to theta. In Hermitian, A is equal to A raised to theta, and in skew-Hermitian, minus of A is equal to A raised to theta. Negation of the given matrix is equal to its transpose conjugate. And one more note for that, the entries of the diagonal elements, diagonal of the skew-Hermitian matrix are always pure imaginary or a zero. Means the diagonal elements, this is the condition of the diagonal elements of the skew-Hermitian matrix. So what is that condition? The diagonal elements of this skew-Hermitian matrix are either 0 or purely imaginary number. Okay, so here in this example you can see this this diagonal 0 and 2i. So 0, either 0, the diagonal elements are either 0 or a purely imaginary number. Okay. And what about non-diagonal elements? They are negative complex conjugate or negation of its complex conjugate. Okay. So 5 plus 4i, the negation of this is minus 5 plus 4i. Okay. Then orthogonal matrix. So what is orthogonal matrix? A square matrix with the real numbers or elements is said to be an orthogonal matrix if its transpose is equal to its inverse matrix. That means if A into A raised to T is equal to A raised to T into A is equal to I. Actually, this is nothing but the condition for A inverse also, right? We can write A into A inverse is equal to A inverse into A is equal to A. So by that property, you can say A raised to T, right? So orthogonal matrix is nothing but when the matrix the transpose of the matrix is equal to its inverse. Transpose of the matrix is equal to its inverse. Then the given matrix is called as orthogonal matrix. Okay. And then last, unitary matrix. A matrix is called as unitary if its inverse is equal to its conjugate transpose. Means our theta, a raised to theta, right? So obviously here we can write here the inverse property, right? So what is that? A into a raised to theta is equal to a raised to theta into a is equal to r. That means which indicates a inverse is equal to a theta. So the matrix is called as unitary when the inverse of this matrix is equal to the transpose conjugate of this matrix. So transpose conjugate is nothing but a bar and t. You can write. Okay. So students, hope so you can understand all these concepts and definitions of these types of the matrix and the introduction section of this matrix. Hope so you like this video. If you like, then subscribe my channel. Thank you.